Hello student friends. Today in this video let us learn some basics about root locus technique. In this I'm going to cover stability concept, angle and magnitude condition. The further steps for construction of root locus and examples will be covered in the next video. What is stability of a system? Stability of a system is nothing but for a given stable input or the bounded input, if the system provides bounded output, bounded is nothing but the finite. For any finite input, if the system provides a finite output, then we call the system as stable. Stability is very important factor to be considered in design of any control system. In a classical control theory, we represent a control system by transfer function. In transfer function, we come across poles. Now these poles play a very important role in determining the stability of the system. The location of poles in the S-plane will determine whether the system is stable or not. There are three criteria in this. The first one is if all the poles of the system lie on the left hand side of the S-plane, then we call the system as stable. If one or more poles lie on the imaginary axis and there are no poles on the RHS of the S-plane, then the system is said to be marginally stable. If there is at least one pole which lies on right hand side of the S-plane, then the system becomes unstable. Now, to understand the concept in a better way, let us take a very simple example where we have a unity feedback system where g of s of the system is k divided by 1 plus s, and it is a unity feedback system, so we have h of s as 1. So what is closed loop transfer function? It is g of s divided by 1 plus g of s into h of s. So when I substitute g of s as k divided by s plus 1 and h of s as 1, then I get a overall transfer function as k divided by s plus 1 plus k. Now to know what are the poles of this system, we first see that characteristic equation. So what are poles? Poles are the roots of the characteristic equation. What is characteristic equation? It is nothing but the denominator polynomial of the transfer function. So in this case, the denominator polynomial, that is the characteristic equation of this system is s plus k plus 1 equal to 0, and the roots of this characteristic equation, that is there is only one root as it is a first order system, so the root is minus of k plus 1, which is nothing but the pole of the system as well. Now here we can clearly see that pole of the system is dependent on k. What is k? K is the system gain or the system parameter which can be varied from 0 to infinity. Now in the next step, what do is we vary the value of k from 0 to infinity and find out what are the values of poles. Now for example, if I put k equal to 0.5, then the pole value is minus 1.5. Suppose if I put k equal to 1, I get pole value as is equal to minus 2, and so on. Some values are substituted and we have developed this table. So when we plot these values of poles in the S-plane, we get a graph something like this. So that means I've plotted all the pole values and joined them together with this orange line. Okay. Now this will determine the path traced by the poles of this system. There is only one pole. As I go on increasing the value of k and plot the points and join them together, it generates a straight line which is nothing but locus of the pole. Now this is nothing but root locus of the system. Now we can define the root locus of the system. Root locus is the path of roots of characteristic equation, that is path of poles of the system in S plane when the system parameter k is varied from 0 to infinity, and root locus is used for analysis of the stability of the system. Now let's see an example. Consider a characteristic equation like this, which is a cubic equation sq plus 2s square plus 2s plus 11k, which is again dependent on k. Now as I go on varying the value of k from 0 to infinity, so every time I get a cubic equation. And what are its roots? Every time I get 3 roots. When I go on plotting that, I get a root locus which is drawn in this graph. So how did we arrive at this is we will get to know once we learn the constructional steps. So that we will see later, just to understand the big picture of the application of root locus. So as of now, we'll take the root locus readily and analyze what happens here. Now as there are 3 poles, there will be 3 branches in the root locus. Here they are represented in blue, green and red. So these are the 3 branches of the root locus. Now if you observe, some part of this root locus is lying on the left hand side of S plane and some part of this root locus is lying on the right hand side of the S plane, and it is crossing the imaginary axis. You can see it is crossing the imaginary axis at k equal to 0.364. That means when k is varied from 0 to 0.364, the root locus was lying on the left hand side of the S plane. When k is made equal to 0.364, the root locus is crossing the imaginary axis, and when k is increased beyond 0.364, it is going into the right hand side of the S plane. That means this will help us to understand that when k is below the value of 0.364, the system is stable. So this will help us to design a system. To make the system stable, we should keep the system parameter k less than 0.364. Now another important parameter or the important concept that we need to learn is angle and magnitude condition. Consider a simple closed loop system shown here, where the forward path transfer function is g of s and the feedback path transfer function is h of s, and we know the closed loop transfer function is given by g divided by 1 plus gh. Now what is the characteristic equation? It is the denominator polynomial, which is 1 plus g of s into h of s equal to 0. So when you bring my 1 to the other side, I get g of s into h of s equal to minus 1. So as you know that g of s and h of s is S domain and s is a complex quantity. So for any value of s, g of s into h of s is complex value. So this complex value is always minus 1. That means when you take the magnitude of minus 1, it is 1. When you take the angle of minus 1, it is nothing but plus or minus 180 degree, or it can be any odd multiple of 180 degree. That is q ranging from 0 to 0, 1, 2, 3 means it is just the odd multiple of 180 degree. So this will tell that basically the root locus is nothing but points or the roots of the characteristic equation. So any point on the root locus will satisfy the characteristic equation, and we have got this angle condition and magnitude condition by characteristic equation itself. That means any point on the root locus will satisfy angle condition and magnitude condition. To understand this concept in a better way, let's take an example. Here the angle and magnitude conditions are restated. So if you read this statement, the values of S that fulfill both angle and magnitude conditions are the roots of the characteristic equation or the closed loop poles, and the S lies on root locus. Okay, any point S lying on the root locus will satisfy angle and magnitude condition. Now we will see a simple example here. There is another concept. What is it? G of S into H of S is called open loop transfer function, OLTF in short. Now for a system, open loop transfer function is given like this. Now what is the value of K such that S equal to minus 0.75 will lie on the root locus. Now how do we get to know the value of K at which the point or the pole S equal to minus 0.75 is lying on the root locus? If we say that S equal to minus 0.75 lies on the root locus, that means it has to satisfy angle and magnitude condition. That means substitute the value of S equal to minus 0.75 into open loop transfer function. This is the expression that we have got. Now first check the angle condition. Now angle of this parameter is clearly 180 degree. So K is a positive quantity and divided by minus 3.0468, angle of this is 180 degree. That means angle condition is satisfied. Next we go for the magnitude condition. So obtain the magnitude of K divided by minus 3.04 this quantity. So if that point S is lying on the root locus, it should satisfy the magnitude condition. So magnitude should be equal to 1. So from this we come to know that for K equal to 3.0468 value, the point S equal to minus 0.75 will lie on the root locus. We'll take another example as like this. So consider this another point where S is minus 3. Now again the same question if we follow, that what is the value of K for which the S equal to minus 3 point will lie on the root locus. We follow the same procedure where we get at S equal to minus 3 we get open loop transfer function value as K divided by 3. Now check the angle condition. So angle of K divided by 3 turns out to be 0. Now what does the angle condition says? At S equal to any point on the root locus, the angle of G of S into H of S should be any odd multiple of 180 degree. In this case it is 0 degree. That means angle condition is not satisfied. So obviously the condition is any point should satisfy both angle and magnitude condition. Angle condition does not satisfy, so it says that S equal to minus 3 will not lie on the root locus. So please make a note here. Always you should first check for angle condition, then go for magnitude condition. Friends, here we will end this video. So in the next video we can see how we can construct a root locus for a given system. Thank you.